film, right? With digital systems, you might not be able to see the changes so obvious because, once again, the algorithm is adjusting technical factors to fit what the radiologists and what technologists like. Yep? All right, good. All right, so changes in mass. Mass is directly proportional to density. Okay? If you're talking about, and I tell you what, why don't you add one thing here? Mass is directly proportional to density and exposure. Okay? And then right next to, under parentheses to exposure, say this is for DR and CR. Huh? Exactly that. Yeah, make an arrow there. Yeah, and we don't mix it up. Yeah, there we go. Go ahead.
Can you repeat that again?
Which part?
What's right after density?
Okay, so density, and then you can put under parentheses exposure if you're using DR or CR. Close the parentheses. Right? Okay, no confusion.
Got it.
All right, good. So, if we're talking about density, then it's this. We understand that this is film, right?
Mm-hmm.
Okay.
Yeah.
But if we're using a digital system, then you have to think more of exposure. Okay. And exposure is what, by the way? No, don't answer. We talked about it. Everybody? What is it? Okay. Anybody else? What is exposure? What does exposure refers to? I'll give you a chance, Gary. Okay.
The amount of photons.
You've been really persistent. Okay, go ahead. Wing it.
Is it like the amount of photons that reach the image receptor? That's
Exactly, exposure. So exposure refers to the number of photons, right? What's another term that we use for the number of photons? Intensity. There we go. Intensity. Good. Good. Oh my God. Yeah. All right. So intensity. All right. So changes in mass. Okay. If we had numbers here, you can see there is a progressive darkness of the image as we move from left to right. So we can assume that changes in mass were done when they did these images, okay? And probably they were going by 50%. Looks to me like they were going by 50%. And so it's a gradual change that you see. Now, if we had done this image and this image with a digital system, probably what you will get is the same image, maybe looking like this, okay? Maybe, it's another maybe, and I don't know the exact technical factors for this image, but probably if you don't have enough mass here, what you end up getting one model with digital systems. Okay? With film, what you get is just a light image. Okay? All right, let's move on. All right, density. Now, I'm done with density and mass, okay? We good? Density and mass, directly proportional if it is film, okay? Mass, exposure, directly proportional in any system, right? Yes? Okay. Remember, and I'll repeat it one last time, when you talk about film, radiographic film, okay, the film that you develop on chemicals, all right? When you talk about exposure, you can also talk about density. With film. Yes? Now, with digital systems, no. With film, yes. It will be proportional, directly proportional. No. So now let's talk about density and kVp. All right. Remember, mass is the primary factor to change density. I said it a million times. That's the first thing you want to do. That's the first thing you want to change when the need for a change in an image is density. You want to change mass. Then comes the other factors. And the second one you should think about is KVP. However, KVP can also be used to change density. Okay, we talked about it. I kind of mixed everything for you guys. As KVP goes up, so does density. Okay, but not proportionally like it was with mass. Okay, it's not going to change proportionally. Okay, so let's move on. So change in KVP results in a change in kinetic energy of the electrons in the tube. Therefore, it changes the number and energy of the photons being created in the beam. Okay? And that will change. That will change the average energy, okay, of the beam. Now, let me take you back to something we did earlier when we were looking at filtration, and we're looking at KVP, and we're looking at voltage waveform. Okay. When you look at the beam, when you look at the beam, and let's say this is 70 KVP, and this is 80 here. Okay? Remember, the average energy, okay, of our beam is going to be somewhere here, right? Is this the average? Yeah. So, what you're doing when you change KVP, the average energy just goes whoop, switches. Okay, you increase the average energy of the beam. Okay, and if you're changing the peak will also change if you change your KVP. If you go to 85, now you stretch it, and the average energy will shift to the right. Okay. A few more things. And this is important. Small changes in KVP can have, and this is not only important. Let me say it here. This is not only important with film, but is very important with digital systems. I'm going to make a little parenthesis. So this is a note aside. So leave this blank like that and a note aside. Digital systems, most digital systems are more, and this is not in your notes, it's not in your book either, so you don't have to write it down if you don't want to. But anyway, digital systems have been built to be more sensitive to changes in KVP than changes in mass. Okay? Digital system manufacturers, they want the technologies to make more changes in KVP than you change in mass. And so the systems are more sensible, okay, to changes in KVP. And a small change in KVP with digital systems can have a profound effect on the image, more than changing mass. Okay? This is just the way the system is. And why do they do it that way? They want it that way so you can still minimize patient exposure. Okay? Make sense? Okay. So now we can go back to this part. Small changes can have a profound impact on radiographic density. Okay. The 15% rule, and I told you this, is a generalization. It's not really a rule. I don't know why. Anyway, that's another subject. It's a guideline, 50% guideline. Changes in KVP impact contrast. Okay? Only change KVP to change the density if a change in contrast or penetrability, add that, or penetrability is necessary. Sometimes you want to change contrast, and we're going to study contrast. That's our next area, and so you'll be able to see that. Okay? So far, so good? Everybody? Monique, what do you think? Yeah?
A little confusing.
Okay, where did I confuse you?
No, it's okay.
All right.
Just a lot of information to digest.
Yeah, no, it's a lot of, yeah, I know it's a lot of stuff that you have to put in place. You will. You will. All right. Okay, when KVP is increased, more scattered radiation, and look, reaches the image receptor. Okay? Not being created, right? It's just reaches more because it has more energy. Reaches the image receptor, which adds density to the film. Okay? However, scatter will also produce more fog across the film. So it's adding darkness, but it's adding fog as well. Okay? All right. More things. All right, now, here's another one. So far, when we changed density, what have been the factors that we have studied? The main one, mass. Second, KVP. Now let's look at the other factors. Okay? The anode Hill effects. You guys remember what the anode Hill effect is? Angela King. What is the anode Hill effect?
You get stronger intensity on the cathode side.
That's the effect of the anode Hill effect, right? But what is the Hill effect? I mean, what you're saying is what most people will say, but that is really the effect. But why do we have that? Why is the intensity higher on the cathode side?
For thicker parts.
Huh?
Or the thicker and thinner parts, so you want higher intensity on the thicker part.
Yeah, but that will be how you apply it. What I'm asking you now is, what is the Hill effect? And she said, okay, the cathode has a stronger intensity, or is intense on the cathode side, right? And you say, well, you put the thicker part. That's the application of what she said. But I'm still asking. I'm still waiting. Just tell me, what is the Hill effect?
The geometry of the anode.
Expand.
Okay, so when the electrons come in and they hit the anode, it's easier for them to come straight back out towards the cathode end rather than go through more anode
Exactly.
and they lose energy.
That is the Hill effect. So because of that is what we have, what you said, and then we can apply it, what you said. Make sense? So because of that geometry, that weird geometry that we have on the cathode, right? Remember, like this, and so this is our target. Because of this, and so you have more photons going this way than coming this way, because they get absorbed on this side, right? So this is the Hill effect. This is the heel. That's what it's called, the heel. Think of kind of a heel upside down. Instead of going that way, it's going down. Okay, but it's a heel. Okay, this is the Hill effect. Okay, and okay, so now that we remember that, alters the intensity of the beam across the cathode-anode axis. Okay, so what do we have? This is what Angela King said. She said that we have a higher intensity on the cathode side. Is that true, by the way? Monique, is that true?
What's the question?
The question is, do you have a higher intensity on the cathode side versus the anode side? Yeah. Say it with confidence. Yes, that's what happens. Okay? And so, what is that going to do? You're going to have higher density on the cathode side. Okay? Density sometimes is up to 45% greater on the cathode side than on the upside of the beam. I mean, this is crazy. I mean, take a look. 45%. That's can be a big difference. Now you're going, I never seen that. And if you're asking yourself that question, I'm glad you are, because why do you think you don't see it?
Software.
That software cleans that up and even evens out the density of the image, so we don't see it. Even with film, was sometimes difficult to see. This is really high, and that's what I'm saying. Density up to, but is less than that. I mean, you might see a change of 30% between one side and the other. Okay, but there is a higher intensity on the cathode side. Okay, more obvious when using larger films or shorter distances. Okay, if you're using, for example, a 14 by 17 and you're using the small focal spot, in a 14 by 17, you see it more easily than if you're using the large focal spot in a large distance. All right. Okay, a few more things. Will not affect density in properly calibrated equipment. If your equipment is properly calibrated, you shouldn't have a problem. You won't see it. Okay, not only because of the algorithm, but because the equipment itself, the X-ray tube itself, is properly calibrated. Okay? All right, film processing. Okay, we have the time, okay, the temperature, and the chemical activity. Just think about it. If you increase the time of the film in the developer or in the processor, what will happen to your density? Let's think about this. This is going to be a nice review. What happens? So, what's going on when your film goes through the developer? Remember, there were two chemicals that I want you to memorize for me. Phenidone? Nope. Hydroquinone. All right. And what do? What's their job, Ethel Cruz? Ethel? She's ignoring me.
Sorry.
I'm used to them. My kids tried to do that, and I get back at them. So what do they do?
You mean the chemical?
Yeah.
They help develop it?
Yeah, but what's going on? What's
Darkening the picture?
okay, good. At the atomic level, what happens?
Is it like the silver or whatnot?
The silver and whatnot?
And the electrons get chemical changes.
You know.
Yeah.
The silver shows up?
I like the whatnot. All right, okay, come on, guys. Help me here. So what happened?
It's reducing.
Is reducing, what is reducing?
The silver.
Okay, so, but how, remember the sensitivity spec and what happened to the sensitivity spec and what happens to the chemicals? What do? Dennis?
The silver highlights are attracted to the sensitivity spec.
But what happened with that part is done. Now you have the film is exposed. So now you have about a bunch of atoms at the sensitivity spec. Now they are surrounded by chemicals. What do the chemicals do? And I know they developed the film, right? I know that. So don't tell me that.
They oxidize.
Ethel?
I think that sensitivity specs have a slight positive charge, and
Oh, you're still
oh, sorry.
on the exposure. John?
They oxidize the silver, so it
Okay,
darkens.
yeah, but what happens? The chemicals do what? Remember, the chemicals, the outside of that lattice is what charge?
Negative.
Negative. And so they are pushing each other because the developer, okay, is negative too. It's abundant with electrons, and so they repel each other, except where? At the sensitivity spec. And so the chemicals begin, and the inside of that lattice is what charge? Positive. And so there is an attractive force. It's something pulling the chemicals. They're going, hey, go through that window. Okay? And that's what the chemicals are going to do. They're going to go through that gate. Okay? And so now we remember that. If you give it more time, if you give it, instead of being there 30 seconds, you're giving it 90 seconds, what's going to happen?
The density increases in those areas.
It's going to get darker and darker. It's going to go in. More chemicals are going to go in because you're giving it more time. They're going to go in and they're going to develop the crystals. Even crystals that were not exposed will get developed. And so now that you have more development, what happens to the overall density of your image?
It's darker.
Woo! There you go. Good. We got it. Now, temperature. If you increase the temperature of the chemicals, what happens to them?
They interact faster and
they become more
Darker,
active. And they,
darker.
exactly, the same thing will happen. They become more reactive. Okay? Right? These are, these are chemicals in, I don't know, some type of drug that makes you go faster, right? Okay? And so now they are overly reactive. And so they are going to expose the crystal. Just same thing as if you give it more time. Chemical activity. Now you have really fresh, new, active chemicals. What's going to happen? Guys, what's going to happen if the chemical activity increases?
That means.
No, back there. Back there, last table. What happens? And it's not only Angela. Christina?
Same as the other two, the image will become darker.
Why?
Exposing more crystals. Not exposing, but releasing them, kind of.
Okay, they're going to have an overabundance of electrons. Overabundance of electrons, and so they are just going to, they want to give them away, even if the others don't want them. They are dumping those electrons because they are more active. Okay, and so the end result of all three going up is a higher density. Right? Good. It's going to be directly related. So you increase temperature, you increase time, you increase chemical activity. In all cases, it's directly related. It's going to get darker. Okay. All right. So good. Now, film and screen combination. So look, this is one that we kind of thought about it when we were looking at this. So now you're combining different films with different screens. Okay. So directly related to density. All right, you guys remember what RS stands for? Yeah, speed. But what is R? Relative speed. So increase the relative speed of your film or screen, the system. If you increase the speed, the RS of the system, and the system includes what?
Film screen.
Film and screen. If you increase either one, you're going to have an increase in density. So when you see a number going, for example, you have a system that is 200 and you're going to a 400. Okay, much faster, higher density. All right? Okay. Anatomical part, tissue thickness. Okay? All right, here we go. Tissue type. All right? If the tissue density has higher atomic number, what's going to happen to the density?
Decreases.
Decreases, right? Because there is more absorption, more photoelectric interaction, right? Jesus, what do you think?
Yes, because more interactions will occur.
What was it?
More interactions will occur if the atomic number is higher.
Exactly. More absorption. Okay, and so density will go down. Good. All right. Pathology can also change, and this is important because it's important for you as an X-ray technologist to read what the patient is there for. Not only, oh, it's a foot. Okay. Oh, it's a chest X-ray. What is it that you're doing a chest X-ray for? Okay. Depending on the pathology, okay, your density will change, and you need to adjust your technical factors. Okay. So there is some pathology there that is additive. Additive means that it's going to add density, anatomical density. Remember, first class when I presented this subject, I said there is photographic or radiographic density, and then there is anatomical density. So there is additive pathology that can add, okay, to the anatomical density, meaning that it will make it more dense. Okay, all right, and so it will be radiopaque decreased density. All right. Okay. Now you can also have pathologies that can be destructive. In that case, you reduce anatomical density. Right?
May I have
Yes.
a question?
Yeah, you may ask a question.
Yeah, because this, I remember in the last exam, you asked about the attenuation,
Mm.
and it relate with the pathology or not?
Of course.
Yeah, if because I remember he's the one the question asked about the straw muscle and too fat, and you
Uh-huh.
asked how about pathology, and you asked about the
Yeah.
attenuation.
How do you answer it?
I choose pathology.
And what were the other answers?
Neuro,
I think it was muscle, fat, and air, right? The pneumo,
yeah,
All
the
right. So
neuro
which one will absorb more? Muscle.
muscle.
Okay. And so what happens to the density? Does it stretch it? That's not what I asked, but what happens now? You tell me now. I'm gonna ask you a question.
Is it, yeah, if it's the thicker the tissue and absorb more and less the density.
Okay, there you go. Less density. And the same thing will happen with the pathology. If you have pathology that is destructive, that it means that is destroying the anatomy. For example, osteoporosis. Okay, the density of the bone goes down, right? And so that's a destructive pathology. If you leave your technical factors like you normally do for a normal patient with no decalcification of the bones, what's going to happen with that image? If the person is decalcified, what happens to that image? It's dark. And so you have to adjust your technical factors. If you see that they are looking for, say, arthritis or osteoporosis, decrease your technical factors.
What's an example for additive?
Additive will be something like, say, pneumonia, okay? Fluid in the lungs, okay? You're adding, okay? You have air and now you have fluid. Which one is denser? Fluid, right?
So because you put the same thing in the when you ask about the attenuation, it makes me confused because the tissue it also decrease the density. Pathology is the same thing.
It's the same thing.
And how can I pick is the best answer?
I need to see the question. I don't remember. What?
So if it's an additive, would it make so it would be making the image lighter instead?
It makes the image lighter. Good. Yeah, that's what it does. And so what do you do your technical factors? Garrett?
If it's too light, then depending if you don't see you have enough penetration, or we're just talking about density.
Hopefully you can catch that before you expose the patient. Hopefully when you see your paper and said, oh, they're looking for pneumonia,
Like which will make the tissue light.
will make the tissue thicker, and so you need more your technical factors.
That'll
to go
increase
up.
if I need more penetration, I'll definitely increase KVP if it makes the image lighter.
There you go. Good. All right. Make sense? How about if a patient with emphysema? What is emphysema? Where are your dictionaries? You're not carrying dictionaries anymore? You know it all, huh? Emphysema. What is it? Emphysema is excess air in the lungs. This happens to patients when they breathe but they cannot exhale completely. They look barrel-chested, and so they are going to have more air than what is normal. So what's going to happen to, well, let's start. What type of pathology will that be?
Destructive.
Destructive. And so what are you going to do your technical factors? Go down. Exactly. So you see that on your request, you go down because it's a destructive pathology. All right. Okay. All right. Anatomical parts. A few more things. Part thickness, variations with large tube angles. Okay. Hopefully you already observed that. When you have an angle, the part that is closer, okay, the part that is closer to the tube, because if you measure from here to here, it's not the same distance than here to here, right? And so just because of distance, okay, this area here, even though in this picture, this is from Carlton, this area here should be lighter, okay? Make a note there on your picture that this is lighter and this is darker, okay, and vice versa here. This is lighter and this is darker because look at all the tissue that you have to go through. So a lot of tissue thickness, density is just the anatomical density is greater here than here. That makes sense? Ethel?
Yes.
Yeah? Good? All right. What do you think, Colleen? I haven't asked you any questions today.
There's, since the
Annie,
X-ray
you're
is going
next,
to
okay?
more
Get ready.
thickness, that means that you'll get a lighter area right there.
Makes sense.
Make sense?
Yeah.
Perfect sense? Okay, good. All right. Okay, casts. Okay, treat it when you have a patient with a cast, treat it as a thicker part. Okay? Now, there are different type of casts, and sometimes the cast is wet, sometimes the cast is dry. When, in general, when a cast is wet, it requires more technical factors. Also, when you have fiberglass opposed to old chalky cast, the white cast, you need less. Fiberglass absorbs less radiation than the old chalky stuff. You guys know what I'm talking about? The white cast? Younger people in this class, you guys know what I'm talking about? They might not never seen it. Yeah, it's white, right? Okay, good. So that one absorbs more than fiberglass.
And most of them today are fiberglass.
The majority.
Or the
Majority.
ones?
What are we supposed to do with the technical factors? Are
You
about to go over that?
increase it. When you have a cast, the minute you see a cast, you need to think, that's a thicker part. I need to increase technical factors. Okay?
Okay,
Now, you have it, regardless if it is the old cast, the old chalky white cast, or if it is fiberglass, you have to increase your technical factors. Now, you have to increase your technical factors with all casts, with the white cast, in comparison to fiberglass. The other thing I said is, if the cast is wet, like, when will it be wet? Well, the patient took a shower or whatever. No, that's not what I'm saying. If they just recently put the cast on the patient, to mold it to the patient's arm, it has to be wet. Okay, and so if it is wet, they want to know. A lot of times they want to know right away before it completely dry. They want to know that it's good, that whatever they are done, the bones are in alignment again. Because if not, they can take it back and put another one. Make sense? And so a lot of times you do x-rays with wet casts. If it is wet, you need more technical factors because the water and the cast will absorb more in comparison to dry. We good?
So do you need more penetration or just more force?
Yeah, what is
Okay. So that in that case, you guys tell me. You guys are the experts now.
More penetration.
I would say more penetration.
More penetration, he says. What do you think, Dennis?
I was just gonna verify. So.
No, but answer me.
Oh yeah, no.
Yeah, what do you
more
want?
penetration.
Okay, so what will you do? What do you change?
Increase KVP.
Oh, okay. Pauline, what do you think?
Yeah, increase KBP.
Okay, sorry. I'm asking Colleen and I'm looking at Rachel. Sorry about that. It's all planned, I'm watching. Yeah. My daughter still thinks that I have eyes inside of my head, so that's why I'm doing it that way. Yeah, but you had a question, Dennis.
So all three require an increase in technical factors, but the wet one requires the most increase, and then the dry white requires the second increase,
look at it
and then
that
the
way.
fiber
Yeah.
still an
Compare-
increase, but
have
not
a
as
group-
much.
Have a group for white cast and one for fiberglass.
Got it.
Okay? The fiberglass will require approximately, if you want, I guess that's what you're pushing me to say.
Yeah.
Why do I use? I won't give you a technique because every hospital is different, but what I will tell you is that you need approximately 5 kVp less when you're using fiberglass. Okay? Approximately 5 kVp less when you're using fiberglass. 5 kVp less when you're using fiberglass.
Great, thank you.
I'll write it down.
Okay.
Is it because,
Yes, Gary.
is it because the fiberglass, well, compared to all the other casts, it's like X-ray can penetrate more easily?
Yeah, and because fiberglass is a lot of air.
A lot of air, okay.
Anything else? Okay. Finish up this section. Filtration. Okay, and then we'll go. Compensating filters. All right. What is the purpose of filtration again? Annie, will you tell us? We were not going home with you.
Reduce the scatter.
Reduces the scatter? How?
Collimation?
Filtration, collimation. You're all over the place.
Okay.
What is the purpose of filtration? Think about it. We're not going home until you answer. What is it?
Filtrate the bin?
I hope that is doing. But what is the end result of filtration?
Is it inside the tube?
Yes, inside the tube.
Yeah, I'm saying that.
2.5 millimeters of aluminum equivalent.
To train it so we get away the power, the photon is not strong enough, so we don't need off focus. Something related to that.
You're really all over the place. You're talking about focus, you're talking.
I don't remember filtration.
Let's see. All right, I guess I'd ask everybody. Monique, you're right close. Yeah, so what's that? So what is the purpose of filtration? Okay, how? Exactly. So it absorbs the low energy photons. Okay? That's what it does. And so, if we were not using filters, okay, images will have a little more density. A little more, not much. And so, in this case, we're not going to think about those filters, the ones that are already inherent in the tube. We're going to talk about compensating filters. Okay? And compensating filters, remember, what do they do? Compensating is saying what? Compensates for what? Body thickness, right? These are the ones that you have uneven when you have an uneven filter. Okay? One side thicker, and so those are the compensating filters. And so you add them when you have the densities are different. Okay? And so by adding filtration, by adding compensating filters, what happens to the density? Point? Decreases, right? Decreases. So inversely related to density, increase filtration, and it will decrease the density. Very simple. Yes.
Does it increase contrast?
Huh?
Does it increase contrast?
Don't even think about that. Yeah. No. It's really not related. Yeah. Grids. You guys know about grids? Okay, we just studied it. Huh? What happens to my grids?
What happened?
Yeah, what happens when you use a grid? Well, I'm telling you. Yeah. Come on.
Reduce scatter.
Reduces scatter. So what happens to the density? Reduces density. Okay, good. Okay, increase the grid ratio. What happens to density?
Goes down.
Huh?
Decrease it more.
Okay, decrease the density, right? Why? Because you have more absorption, right? Okay, you guys are good. All right. Okay, let's just stop here. Beam restriction. Okay, this is the time, guys, where everything that we have done so far, you have to really put it together. So to really have a good understanding. It'll be good to have all of that before the final.